So you got those blowers, so they provide the air, so that they should have. They're probably running on a set point control where they say, okay, I've got, I'm up to 3, slow down the blower. So there's got to be a control there where they'll enter in a set point, and then they'll try to be controlling that. So since you've got two, I don't know how they control them individually. I'm not really not that familiar with it, but whether they can control it, because one guy at 5 and the other guy at 2. Eventually, it all gets mixed up, but so they have some sort of individual control. So they have each fire reactor has its own monitoring, DO, and pH control. So, like I say, from the bioreactor, from the aerobic zone, it goes into the post-anoxic zone, and again, the low oxygen levels promote the denitrification. So, we're talking about the bugs and all that. So we want to monitor the aeration. Obviously, we're monitoring the level control. Well, that's more for hydraulics. We're monitoring the pH control and sludge control. So we don't want our MLSS getting too high either. So when we start, so wastewater is pretty low in solids. As we're developing the whole mixture, we're taking out clear water, and all the solids remain in the system initially. So we're putting in solids. Then we're taking out clear liquid, and all the solids remain in the water. Eventually, that mass starts growing, and then if you have, so you need enough to bacteria and everything to treat the incoming water. But if you have too much, not good, or if you have too little, not good either. So if you have too much water coming in and not enough bacteria, stuff just gets passed through. You don't get the treatment. If you got too much bacteria but not enough food, they starve. So it's kind of a whole combination of things. But that's why you want to control the MLSS and not your waste. So you'll look, okay, it says in theory you're supposed to waste this much, but if you're wasting too much, then you're going to be taking out too much bacteria. If you waste too little, your solids going to go up, then your pressure is going to rise. So it's a whole kind of a learning curve. The aeration level, it should be like, because that's controlled by, we don't control that, it's by the SCADA system. And there will be a set point in there, so you just want to make sure. Like I say, it's probably, I don't know whether to set it to 2 or something. 1 to 2 is kind of the optimum DO level in the bioreactors. Now they got talk about level of control. Well, it's all by gravity. So once it's going to overflow, and then it's going to go in the post-anoxic zone, and then that's going to flow in the membranes. So that level in the post-anoxic zone, I believe, it creates your demand, your trim level. And so as the level goes up and down, as flow reduces in the night, that level will go down, and they'll say, okay, slow down the membranes. So we're controlling the pH. Normally, don't in domestic, you really don't need to add anything. But I think here we've got what, ability to add caustic.
Yes, sodium hydroxide.
Yeah. So probably may or may not run very often. It shouldn't, unless someone's dumping something into your system. But the pH should be relatively stable in the overall system. Sludge control, again, the wasting. You want to, looks like here, maintain a concentration of less than 8,000 milligrams per liter. Like I said, there's a interface that will let you set the how much you want to waste, what time it starts at. It's going to be the flow rate. You can't control the flow rate because it'll just open up a valve and it'll just flow whatever. Because I think it's a 3-inch line versus the garage was a 6 or 8-inch line. So hopefully it doesn't plug off. So that, like they say, the valve, the wasting valve, will open up at preset time. There's a flow meter on that line. Say, okay, set point was 1,000 gallons that we want to waste, and then it'll close off the valve.
That's nice. I haven't seen one that can operate on a schedule yet.
But we'll have a look. I'm pretty sure. That's the standard that we usually do. So micro-C is a source for external carbon required for denitrification is added. So they're adding here in the post-anoxic zone. And then I guess you've got either it's pace to flow, or you can say, okay, run it for X amount of time. So we'll go through that. So either I can say pace to flow, or you can set duration every 0 to 60 minutes. And there's an enable button, looks like here. So if you don't want to add it, you don't need to add it. So yeah, you've got dosing for caustic dosing for pH control, and then there'll be triggers that you can turn it on at a certain pH and turn it off at another pH. So that's all automatic. You just set it up, and then it'll just you don't need to be measuring it on a regular basis. It'll do it on its own, measure it, and then knows whether it needs it or not. Okay, so the next thing is the ultrafiltration trains. So the UF systems has so you've got the membranes, you've got a process pump, back pulse pump, the aeration blowers, you've got an ejector system, recirculation system, air compressors, and chemical injection system. So that's what the UF is composed of. You've got your actual membranes that do the filtration. The process pumps are the ones that pull the vacuum to draw the water through the membranes. The back pulse tank that's where the source of the water when we're doing a back pulse. Are you guys familiar with the term back pulse or?
Mm-hmm.
Okay. It's like a sand filter, whatever. You reverse the flow of water. So we're taking that clean water, we're reversing the flow, and instead of sucking in the water through the membranes, we're putting the water inside the membranes and then reversing the flow to blow off the solids and build up on the membranes. Now, normally we're running in what's called relax mode instead of back pulse mode, especially at the start. We found that you don't really need to do back pulses. So we do a production cycle, and then we stop the production pump, and then we either do a back pulse where we reverse the flow, or we do a relax mode. So basically, relax is we just stop production and we continue aerating, and the membranes keep shaking and knocking off the solids. And we found, they found over the years that, especially on new membranes, you really don't need to do back pulses. They will keep clean, and you don't need only when the pressure start getting higher, or you got your MLSS is too high for some reason. Then you might need to do back pulses, but typically we just do a relax instead of a back pulse cycle. The membrane blowers, so we have our own blower system that feeds air to the membranes. So they are putting in air in the bottom of the membrane cassettes, and then they're bubbling through the membranes and keeping that clean. Now the term seaweed, I guess somebody said, "Oh, that looks like seaweed in the ocean," so it's kind of shaking, and that's why someone said, "Oh, that sounds like a good name." So it was and because the company was called Xenon Z, so that's why they call it seaweed. So it's just I don't know what you call it, what the term is, but that's how someone come up. Oh, that looks like seaweed. Oh, we'll call it seaweed. So that's all the name. And the air compressors are for running the actuated valves, so to open and close the valves. And we've got chemical injection. So the chemical valves for injection of chlorine and citric are on our pump skids, but the chlorine system and the actual tank makeups are controlled by SCADA. So we would send them a signal, and they inject the chemical around the pumps and all that. So that's in a nutshell the ultrafiltration. We're just pulling the pump pulls the vacuum, so it draws the water through the membranes, and it's a negative pressure. So when we're drawing, it'll be negative. So when we're running, you'll see it running. It'll show a negative pressure on the system, and when we're back pulsing it, the pressure goes positive. The pumps themselves are reversible, so they go forward and reverse to create either suction or create the pressure to do the back pulse. Back pulse tank is filled automatically. There's levels sensors in there, controls that will fill it up, and then we draw from it, and then when it needs to be refilled, it'll just automatically.
We don't need any to add anything.
It goes usually after midnight, just once a day. We'll have some dosing to just prevent stuff from going in there, because it's kind of a side stream. Some places where it's an overflow tank, so you don't really need to, because it's just overflowing and then going out to UV. Here it's just a side stream for filling that tank when necessary. So yeah, so it'll be like once a day at midnight we'll dose hypochlorite to prevent any growth in there.
Okay. I know I used to have to use bioxide because when we did the chlorine, we used to use powdered granulated, I should say, and then mix it, and so you sometimes could end up with a chlorine film over the membranes, like over time.
RO don't like chlorine, first off, so
correct.
That's probably why.
So we use the bioxide, okay, so that's why I just wanted to
Yeah, RO do not like chlorine, so you've got to add SBS, whatever, sodium bisulfite to knock down the chlorine in the system before, because if you had too much chlorine, then you got to replace the membranes. But, here, I think you got these membranes. I don't know what it is. You got like 1 million chlorine hours or something before. So we use chlorine to clean the membranes here, so it's not not really an issue. So yeah. So again, the membrane aeration blowers, they're the ones that provide the air to keep moving the solids. It's a mechanical system. There's no valves where you turn it on off. the air goes into the bottom of the membrane header at the bottom, and then that creates the bubbles. It's more like, I guess, explain to me, it's more like an aquarium where it's somehow the pressure is created and releases bubbles. And air is constantly going in there, and then it just mechanically opens up as the pressure gets high enough. It's kind of cute. So that's why they call it leap aeration. It used to be a general. We were owned by GE, so every time they call everything, it was some major innovation. They called it a leap. So they've got like leap engines for their aircraft. They've got the leap diesel for the train. So we call this leap MBR because of this innovation. Before, we used to have cycling valves on off. Every 6 seconds, the valve would turn open and it provide air to one side, and then it close, and then provide air to the other side. So what do you think happened after running a valve 6 seconds for 24 hours?
Every 6 seconds?
Every 6 seconds, valves would go. We never found a valve that could survive for
Yeah, a lot of maintenance.
So someone came up with this leap aeration where there's no mechanical moving parts. It just pressurizes inside this contraption. You know how, like I said, I don't even know how it works. It bubbles up and on. Wow. It's pretty cool, I think.
Sounds like almost like a ductile valve.
There's no
The rubber's pinched, and then when it gets too much pressure, the rubber just has to force out.
and the beauty, there's no moving parts. There's nothing actually moving, expanding, whatever, laying off. I'm not sure. It's like I said, I'm not sure how the principle works. All I know is it does its thing, and with no moving parts, there's no maintenance on anything, nothing to replace or do. Another key thing is the air ejectors. So the air ejector just draws air out of the system. So we'll show you when we go down there. There's a high point in the line. So the ejector will run, especially when it's in standby. It'll run, open up. It'll draw the air out of the line, and basically flood the whole pump. So if there's any air buildup, and then we also constantly run it. I think it's once every 6 minutes we'll run that ejectors. If there's any air buildup in the system, it'll pull it out. Because if you got air trapped in there, the pump won't pump. It'll just be airlocked. So we run that ejector. Especially if you take out a cassette and you do work on it, you've got all that air trapped in the system. You need to get it out. So the ejectors you just can run them manually to remove any air in the system. And then we've got recirculating pumps. So again, we're typically wastewater's coming in from the post-anoxic zone. So we're kind of moving it around. I think it's like 4Q. So for every, say, 100 gallons of permeate, we're probably bringing in 500 gallons. So because we're going at 4Q, so we're recirculating at, say, 400 gallons, and we're permeating at 100 gallons. So we're constantly moving that stuff around, and then that returns back to the pre-anoxic zone, and it makes its way back around the system. So that's what the RAS is for, because we're concentrating in that membrane tank, so we need to move those solids back to the system where it's retreated, and also otherwise, if you did RAS, you just come quitting. Excuse me. Because you're pulling in solids and water, taking out water, and if you never remove those solids back to the system, it would just be like. So if the RAS pumps fail, the system faults. It won't run. You can't run without RAS. You can't run without aeration as well, because if you're not aerating, you plug off the membrane. So any of those things will fall. Unfortunately, there's a million alarms. If your pressure is too high, it faults. If you've got no airflow, it faults. RAS pump faults. If your permeate pressure flow is too high, it faults. If it's too low, it faults. So there's a whole pile of things that we monitor in the system. And obviously, the air compressors we use to provide air for this air valves, and also air for the ejector. So the ejector runs on air. It's basically a Venturi, so it needs air to run. So no air compressor, you got low air pressure, system faults too. So that'll show up on the screen. And then last thing, we've got chemical injection systems. We got sodium hypochlorite for cleans, for maintenance cleans and recovery cleans. So the sodium hypochlorite is for removing organic materials off the membranes. Citric acid is for dissolving if you got iron, calcium, magnesium, that sort of thing, any kind of inorganic. So typically we're doing more organic cleans, so we're doing more hypochlorite cleans and acid cleans. You may find acid cleans you don't need to do them over a period of time. We don't really need to. I don't know, maybe get studies on this water, but typically we supply it with acid and hypochlorite cleans just to be on the safe side. So you may or may not need to do citric cleans. They're not very obviously a lot less. We add micro C to the system. That's to enhance the denitrification process, and then we use sodium hydroxide to adjust the pH level to keep the bioreactor in check.